So hello everyone and welcome to the IFST Scottish branch event, Net Zero Gin, Low Carbon Food Production, Making More with Less. My name is Ruth Burt. I am chair of the IFST Scotland branch and I welcome you all here this evening. Thanks for your time. The Scottish branch committee has been looking, considering topics for running a webinar. And we thought that this was very timely, particularly because the UN Climate Change Conference, COP26, will be held here in Glasgow in November this year, fingers crossed. But also because a global climate emergency has been declared by the First Minister with a commitment towards net zero by 2045. So with food production responsible for about a quarter of the world's greenhouse gas emissions, this seems a very interesting topic, a very topical topic for us to be considering today. And also particularly because Scotland is lagging behind in our rate of innovation activity around climate change. But luckily tonight we have two excellent speakers who are here to showcase the initiatives of their organisations with innovative solutions with respect to climate change. Next slide, please. So the webinar is being recorded and will be shared on the IFST website. Feel free to make comments and ask questions throughout the webinar using the Q&A function, which will be at the bottom of your screen. This can also be used in the case of any technical difficulties. Fingers crossed we don't have any of those. There'll be a Q&A session presentation where we'll respond to as many of the questions that have been posted, and Jonathan Wilkin, Secretary of the IFST Scotland branch, will ask the questions of our speakers on your behalf. Our speakers today are Professor Derek Stewart and Kirsty Black. Derek's bio is on the IFST webinar promotion for this evening's event, but just a couple of top line points. Professor Derek Stewart is the Director of the Advanced Plant Growth Centre at the James Hutton Institute. He's responsible for developing research opportunities in agriculture, food and drink supply, value chains, production systems, biomass waste valorisation and the biocircular economy. He has over 30 years in career pursued in crop production with his work reflected in over 170 reference publications. He currently holds the chair of the food chemistry at Heriot-Watt University. So welcome, Derek, and thank you so much for joining us this evening. Kirsty Black is both manager and distiller at Arbikie Highland estate, a field-to-bottle distillery located on the east coast of Scotland, producing an award-winning range of gin, vodka and whiskey. Sounds blissful, Kirsty. Kirsty will give more details of her background in our talk, but she's currently undertaking her PhD studies in Arbikie University and the James Hutton Institute. So they were our initial sort of introductions, but without much further to say, I think I'll hand over to you, Derek. Thank you.
Okay, thanks, Ruth. Okay, good evening, everyone. So I'm going to talk today about low carbon food production and give you a very whistle-stop tour about what my institute and some of the teams I'm overseeing do in this area, whether it's for reusing waste or actually producing food through low carbon production processes. So first and foremost, what's the problem? Well, I think we all know what the problem is. There's just too many bloody humans. We have limited resources and the population is increasing. 8.3 billion by 2030 or 9 billion by 2050. And to feed all those, certainly for 8.3 billion, we need 50% again of food. And to do that, they need more energy, land, water, but all during a period where we've got soil erosion because we've been treating the soil not particularly well, and we've got reducing biodiversity. So we need to change our processes. There's a double whammy, of course, then, where we've got climate change ongoing, and we need to change our systems and processes to deal with that, both mitigate and adapt. But as time goes on and population increases, the Intergovernmental Panel for Climate Change suggests that between 12 and 40% of the Earth's land surface will be developing new climates. So that's really going to play havoc with existing food production systems. The other thing as well is the nations evolve and change, and the predictions are there's going to be 3 billion more middle-class consumers, a lot of whom are coming from plant-based food economies. They're going to be wanting meat, which will exacerbate climate change, but also they've got a lot of spendies that they want to be buying consumer goods, which again, a lot of these are produced using linear production systems. So we're facing a whole set of problems we need to deal with, and food's in amongst that. So we need to rethink about how we do that and embrace this thing called the circular economy, more of which in a minute. And basically what that means is preserving and enhancing natural capital, basically the resources we've got. We need to make sure the processes that we're using and the yields of all those processes are optimized. And what they call foster system effectiveness and designing out negative externalities. Basically that means no dead ends. So if there's a waste, we find a home for that waste and we use it. So the poster child for the circular economy is the Ellen MacArthur Foundation. I'm not quite sure if my mouse is visible there, but there we go. It's on the right there. But what I'm going to mainly talk about today is the circular bioeconomy, and it's how many times we can reuse biological-based systems, ideally in the food system, and there are many examples of that today. To introduce the concept of the circular economy, we're in a fossil fuel economy, but trying to move away from it at the moment. And basically what that does is you produce oil and gas, you create or crack that down to create what's called cracker products. These are fairly simple molecules like ethylene, propylene, butadiene, aromatics. Many of them are plastic monomers. Then they're made more complex, cracker plus one. So you add different chemistries to them. And that basically helps feed almost all of your consumer goods. I mean, most of you are watching on a webcam now, which has cracker plus one products in it. You've got screens that are in there. You'll be probably wearing fabrics that have cracker plus one products as well. But we can produce these from renewable feedstocks, but they take a bit more energy. They take capital cost because they've got different processes. So we're starting to evolve into these, and these need to be made very efficient first before we adopt them. But how do they work? Now, there are existing supply chains that can take straw through catalysis, create ethylene glycol, and using bio-based phthalic acid, create PET. PET is ubiquitous in the world. And you can just see some of the products now that are made from PET, but these can all be made from simple things like straw. But what we need to be able to do is crack that straw down from the straw material into these products using systems called biorefining. Now, biorefining, if you put biorefining into Google and look on images, you'll get lots of diagrams like these in there. And basically, they're just extraction schematics. Biorefining and bioavailable products basically means cracking down the raw material into useful feedstocks and chemicals. What it tends to involve is wet or dry milling and different fairly facile and well understood extraction processes. So how would this work in the food systems? Well, some of the stuff I've done with partners and friends in this case, the Danish Technical University, we looked at what would happen if you buy a refined bran that's generated from when you mill wheat. So we know this is an old process. You mill wheat for flour, you make bread. Centuries, millennia old. But actually, if you apply biorefining to the bran, you can make all of these components. And these are vastly useful as food ingredients, and we've got a huge value. And in fact, the value of those is about tenfold the value of those. All of these extracted from the bran products is about 10 times the value of the flour. And on a more schematic basis, this is what it looks like. So the wheat bran cracks into insoluble and insoluble fractions. You can start to create prebiotics, protein-rich fractions, oil-rich fractions, all of which can go into general or high-value foods, and actually some of them go into cosmetics. So we've got processes then that can take biomass and crack it down and put it back into the food chain. We need to know what these biomasses are. And in Scotland, I helped draft the biorefining potential for Scotland, a big project funded by Zero Waste Scotland. And what it did is it wanted to map what the bio-wastes were and where were they. What this allows you to do then is construct processes where the waste from one could be a feedstock for another. So for example, there's a lot of bakery waste, often concentrated in one area. So breaks or these companies like that will have a lot of bread wastage from cutting sandwiches and things like that. That bread waste can then go back into the brewing industry because the bread can be cracked down to glucose and be supplemented into for fermentation into alcohol. So once you get that concept in your mind, what we do is we map things out, and this is a really busy slide, one to look at at your leisure if you wish. So we mapped lots of different wastes on the basis of local authorities and where they're produced. So that's all the data dumped into one slide. So if we go back to that PET thing I was talking about earlier on, so that was based on straw. So if you wanted to build a biorefinery that was going to crack that straw down for feedstocks to make plastics, you have to find out where most of the straw is made. Well, clearly what you would do is create a biorefinery in Aberdeenshire then, or in the analogous areas close by. Similarly, when you're thinking about adding value, you've got to think about just the physical aspects of your waste. So here's 1/10 of a ton of straw in a van. If you simply mill it down, that's the same thing on the right. So you don't want to be transporting the one on the left, you want to be transporting the one on the right. And this is crucial because what it does is it pushes that process back to the farm level, which means the farmer then gains value. They're always the loser in these games. But in this case for biorefining, a lot of these processes can be done on farm. We're doing a lot of work on that. Another example of this is probably one of the commonest food crops. Just looking at the time now, some of you may have had your food already and probably potato has been in it. So we know what potato is used for, but the above ground is a real fantastic chemical feedstock, which can be biorefined, and simple biorefining will extract the protein out of it, which can go back into aquaculture or animal feed. But you can also take out some wonderful chemicals like this, solanisol, which goes into really high-end cosmetics as well, or it's actually got bioactive aspects, which we're patenting at the moment. So there's huge value in waste at the moment. Again, you can map it out. Where would the potato Holland biorefinery be? Well, it's going to be in Angus, Perthshire and Kinross. This is my neck of the woods, and actually we're chasing that opportunity at the moment. So we can see from a lot of these chemical feedstocks, certainly for a lot of the big field crops, there's common ones. So all these ones like barley, potato, beans, potentially sugar beet, they've got common polymers within them that can be cracked down into much more useful, smaller molecules that can then have value added to them back into the food chain as ingredients, as antioxidants, as stabilizers, as thickeners, or they can go into another sector. So ones where you get more speciality, ones going into the food chain are, for example, in soft fruit waste or co-products. These supermarkets take class 1 fruit and the class 2 fruit just doesn't go anywhere near it. So the grower has to find other alternatives. Well, the components within things like raspberries, strawberries, black currants, all of these, those natural chemicals have got ready homes as sustainable colors, and someone's actually made a sustainable purpley blue hair dye for out of blackcurrant anthocyanins. So they can be ingredients or antioxidants, they can be dietary fibers, I'll talk about abrasives in a minute, or they can be simple botanics. So you can go into the distilling aspect, start adding flavors into unique gins. The other one is cherry's quite a small industry in Scotland, so the level of class 1 fruit isn't as high as it will be. So they've got a lot of non-class 1 fruit that needs to be valorized. So on farm, they can process the flesh into, or extract them for colorants, process them in alcoholic drinks or foods like yogurts. But that leaves things like the stems and the pits, the stones. Well, you would think the stems, there's no value in that. But actually, if you go to the countries that comprise the old Ottoman Empire, cherry stem tea is actually quite prized. So they've got an immediate market. And the guys here who have these stems are now shipping them over to Turkey. Similarly, for the stones within these, they are already replacement following different levels of milling into cosmetic dermal abrasion products. And what they're doing there is replacing microplastics. That's a fantastic win-win right the way through on that one. And similarly on other common Scottish crops like oilseed rape. So we grow a lot of oilseed rape. It's processed into oil. You've then got the pulp left, which is a protein-rich pellet or cake, they call it. And that's generally livestock feed, so it's quite a low value. But if you extract some of the proteins out of that using proprietary treatments, you create a protein that's got exactly the same properties, physical properties, as gluten, and it gives bakery the bounce, but it's non-allergenic. So apologies for the appalling cooking here. It was all men that were doing this in the lab. It's a horrible sexist thing, and they weren't really interested in what it looked like. But what you're seeing here are supposedly muffins. So the ones on the left are wheat with gluten, the ones on the right are wheat without gluten, and the ones in the middle, we've added this protein and it's given the bounce back. It's made the muffins rise. We're shifting to an economy that's seeing less meat being consumed, but still the demand for nutrition and protein is there. So we're starting to see things like fava bean and other protein crops coming through. And this is where work we've done with Arbikie and Kirsty may touch on bits of this, or maybe not. So when you biorefine or start to mill beans, you get different fractions throughout that. So you get very rich protein fractions, and a lot of the time they can go into humans, and there's a huge demand in North Africa for that. You'll get a less clean version that's contaminated with starch that can go into fish food, but you get high starch fractions that go in that can be used into bread making again. But that starch can then be used in fermentation industries. So it can start to produce beer. It can be a cheap feedstock for neutral grain spirit. But the hulls of the beans, and anyone that's eaten any type of beans will know if you actually cook them and pop them, you get the inside comes out and you're left with this hull. That hull, when milled up and slightly wetted and extracted, creates a fantastic soluble dietary fiber that can go into breads, and you wouldn't know it's in there. So there's some fantastic uses getting made. So I've given you a feel really for bioprocessing as to how wastes can be used either from the food industry and going back into it, or primary production, and it could go back into the food industry. There are other hidden wastes as well. And this leads on to primary production that I'm going to talk about now. So in a lot of industries, you get waste heat and CO2. The best uses for those can be to produce even more crops, particularly ones that are harder to grow and they need a higher temperature. And if you add CO2 for annual crops and you can keep pumping CO2 in, the biomass production or productivity just lifts very significantly. So as part of the project I'm director of, the Advanced Plant Growth Centre, which was funded from one of the cities deals, what we're looking to do are use things like precision controlled environment technologies to really ramp up how we produce food. And this is precision control across the piece. This could be outside or inside. So we've done a lot of work already looking at outside precision technologies. So this could be GPS-based systems on combine harvesters. It could be predicting growth of crops and maturity and disease and water use using satellite and drone-based systems, and they generate maps like that. And you could see from this, there's clearly differences in that field, but by visual analysis, you wouldn't see any difference. And what that then does is generate data that can go to the farmers on app-based systems. But what we're looking to do is change the paradigm in how we produce food and use things like vertical farms, like you see on the bottom left here. And as part of the Advanced Plant Growth Centre, vertical farming is very much part of that. It's the ultimate aim in controlled environment agriculture. So it's the ultimate progression from polytunnels. You're controlling everything that's in that. So as part of this centre, this new centre that's starting, we're also looking at next generation controlled environments, which means we can dial in climates now from different parts of the world, or ones we think the world will change to forward, look to see what crops we need to be growing in those environments. Developing sensor-based systems that we can assess these things very fast and in real time, and then develop new post-harvest storage systems, because once you've grown it, you don't eat it all at the one time. You then need to be able to store and eke this thing out for processors. So there's a huge impact on food all the way through this process. So as part of this, I'm working with a whole plethora of different vertical farming companies across the world. Ones like Vertical Futures, who are looking to develop very compact type stacking systems. You've other ones like Liberty Produce, which is a much more modular approach. Liberty Produce are actually based on the site here at Dundee. And there's a one where you can actually build into derelict urban systems, because you can adjust the height on all these modular systems that they've developed. And then you've got the other ones that are absolute state of the art, like Intelligent Growth Solutions, that have got the tower systems. Their stuff really is tomorrow's world. And they're developing systems that actually humans won't go into. And they're developing robots that will go into that system as well and come out. I mean, the benefits in all of these are just enormous. The lift in productivity in most crops can be transformative and fold scale, not just percentage, fold scale. And the ability to grow 24/7, 365 means that it gives you the equivalent of these vertical towers on we've got 4 towers in there. That's about 15 meters high. 2 of the growth towers within the system, and the Dundee one's equivalent to a hectare of land, but on a footprint that is tiny by comparison. And also the efficacy of these systems are enormous, because growing, for example, lettuce as an example in the vertical farm will use almost like 1,000-fold less water than it would do if you were growing it outside. So the benefits are enormous. And all these vertical farm systems are now being looked at to be run on renewable energies, whether it's from coal mines, ground heat pumps, solar, and wind. So once that energy piece is squared, they will beat everything else. So coming towards the end of this, what do these new production systems offer? Well, if you think about a vertical farm, what you can control is the light, the nutrition of the crop, the temperature, the gas that's growing in, and the plant material that's in there. So even if you think of some of the components within each of those and vary 3 settings of them, that gives you a total of about 60,000 combinations you can make. And each one will have a different taste, texture, and appearance from the same single plant. So the opportunities this offer are absolutely enormous for food production. So we can start to create bespoke foods using this, or the same food, but extremely efficiently. So hopefully what I've given you a feel for is that we can significantly maximize co-product use in and for the food and drink industry. Things are changing. We can produce primary products and feedstocks much more consistently and with an on-the-dial quality. So in vertical farming, if I produce one crop today, the one 10 years hence should be exactly the same quality, because I control everything. And all of this by using renewable energies, and certainly for the waste aspect, allows us to deliver to low carbon production agendas, so delivering to net zero. Thanks for your attention.
Okay, so yeah, good evening everyone. So today I'm going to talk about the potential of legumes as an environmentally sustainable raw material to Scotland's food and drink industries. Before I do that, I'll just give you a bit of background to me. So as you've heard, I'm the manager of Arbikie Distillery, which is on the east coast of Scotland, located just between Arbroath and Montrose. So we're a farm-based distillery where all the raw materials we use to make our spirits are grown on the farm. So the crops are all taken in from the farm and leave as a bottle of vodka, gin, flavoured vodka or whiskey. So we use potatoes, wheat, barley and rye to make these products that you can see on the screen. And then most recently, we've started to grow and use peas, but we'll get to that in a bit. As well as Arbikie, I also sit on the examination board and awards committee for the Institute of Brewing and Distilling. I co-chair the Green Economy Can-Do Collab, which aims to support organisations in reaching net zero. And I'm also doing a part-time PhD for the James Hutton Institute and Arbikie University. Now, across all of these sort of areas, there is alcohol at the heart, but the need for sustainability is becoming more and more the focus of these over time. Right, so now let's go back to 1909. So in the summer of this year, these 2 gentlemen developed something which has been credited as the most important invention of the 20th century. So I don't know if anybody will have a guess what it is, but if I tell you their names, that might help. These men are called Fritz, Haber and Karl Bosch. And the process is known as the Haber-Bosch process. So don't worry, I'm not a chemist. I am very much a plant scientist and distiller, so I won't go into these individual steps. But the key to this is that this synthesizes ammonia from its elements of nitrogen and hydrogen. Now, ammonia has a number of different uses, such as the production of explosives, but it's the one that's increased the world population rather than decreased it that we're interested in here today, and that's fertilizers. So fertilizers are food for plants. They allow us to grow more crops with greater yields. So Scotland's a good example of that. Now, nearly half of our arable land is used to grow barley, and a big chunk of that is destined for the brewing and distilling industries. To achieve the quantities and quality of barley that we need, however, you also need a lot of fertilizer, and that comes at a price. As you can see here, there's both a financial, so in pounds, consequence, and environmentally in the emissions associated with its use. So to put this number in perspective, it's the same as 100,000 cars driving around for a year, and that's just one crop that we grow in 1 year. And the emissions are just the start of it. Fertilizer use has also been shown to pollute our air, water, and soils, as well as causing a reduction in biodiversity. So there's no real getting away from it. Plants need nitrogen. But despite nearly 80% of the atmosphere that we breathe, so the air we're breathing in right now is nitrogen, it's in a non-reactive form, so it's unusable by plants. This is where legumes come in. So legumes such as peas, beans, and lentils are different from most plants. So they're able to fix this non-reactive nitrogen from the air via a symbiotic relationship with bacteria that's found in the nodules in their roots. They can convert it from non-reactive form into reactive nitrogen. So this allows legumes to be self-sufficient, so they don't require nitrogen fertilizer, and in turn you're able to produce a crop, whether that be a whole forage crop for animal feed or a pulse crop, again for either animals or humans, to eat with minimum inputs. So in addition to legumes being able to support themselves, they can also make the nitrogen available to surrounding plants, and also leave residues in the soil, reducing the need for fertilizer use on subsequent crops. So by understanding this, we can say that legumes offer nutrition for animals, for humans, and also the soil itself. So all this background is the starting point of my PhD. So here we are looking at the potential of supporting traditional crops, so things like barley that we grow a lot of in Scotland, with legumes instead of using fertilizer as a nitrogen source. So this is something we call intercropping. Critical to this working is that cereal quantity and quality must be maintained, but then there's also needs to be a market for resulting legume crop, and ideally a high value market at that. So being in Scotland, we naturally turned to alcohol production. So as you heard from Derek, most seeds have different fractions, mainly starch and protein. So brewing and distilling only uses the starch component. So we can convert that starch into some high value products, but then we also have the added benefit that these production processes result in a co-product rich in protein, which has value to the feed industries as well. So we can look at each of these areas in a little bit more detail. So first up is intercropping. So I said that's when you grow a mixture of 2 or more crops in the same field. So this photograph here, you can see it's been randomly sown with peas and barley. So the peas are the sort of round-leaved plants with the white flowers, and then the barley is the grass-looking plant. So being in Scotland, we've had to pick crops that not only have a market here, but will survive in our growing conditions and short growing season. So 2 of the main cereal crops are barley and wheat, and these have been matched with peas and beans. Okay. So the method of intercropping increases diversity. So immediately you have 2 instead of 1 plant variety in the field. But this in turn increases pollinators, insects, and the biodiversity both above and below ground. Intercropping also results in better use of resources such as nutrients, lights and water. It increases the yield per unit of land. So we use a measure called land equivalent ratio, which looks at a unit of land and the yield if you grew each crop separately compared to together. And also intercropping can help suppress weeds and reduce soil erosion. Okay, so here's a high-level diagram of the brewing process. So whatever type of alcohol you're making, it's produced by yeast fermentation of sugar into carbon dioxide and alcohol. So our normal raw material in brewing is malted barley, and it's full of starch. So the brewing process aims to extract the starch, break it down into simple sugars, which can then be used by the yeast during fermentation to produce alcohol and the carbon dioxide, which makes beer fizzy. So the one other step in this flow is the boil, which is where you add hops and flavour develops. But the most important step for us today is this one called mashing. And this is where we're breaking down the starch into the sugar, which can then be fermented. And at this step 2, we're also removing then soluble material and making that co-product called draff, which is rich in protein. So we're proposing that we change this sort of standard brewing process and we add in a legume. So here, all the work today has been done on faba beans. So faba beans are a very good legume to grow in relation to soil health, and they have very deep roots, therefore they improve the soil ability to a deeper level. And some of the other further reasons for picking faba bean are listed here. But you can see we're really still talking about things like reduced greenhouse gas emissions, improved biodiversity, and improved soil health. The use of legumes in brewing is not actually new. There's references in historical books. There's one called The English Housewife from 1615, which instructs someone how to make beer from peas. But there was a new tax law introduced in the 18th century that meant that UK commercial brewing could only use malted barley. So therefore legumes were really confined to brewing at home. Nowadays, legumes are really not used at all. It's very limited use and really for special edition releases where they're being used for flavour rather than the conversion of the starch to alcohol purposes. Some countries do tax beer in relation to the amount of malted barley present. So the perfect example of this is Japan. They're very strict. They have a whole separate category of beer, which has no malt included. And it's basically made from fermenting sugar, but adding in something like soy protein. So soy is a legume as nutrition for the yeast. Okay. So as I say, we've supplemented and replaced some of the barley with faba bean. Fortunately, you can't just replace them and treat things exactly the same. You still need to adapt the process for the specific starch that's present and the enzymes needed to break it down. But we've worked on that. We've produced this paper here, which is the optimized method for processing. It's in the Journal of Institute of Brewing. And also, and probably more, as there's no point in doing this if it doesn't taste any good. So we found that including beans in the beer had no impact on how consumers interpreted the flavour of the beer. We've had a number of different commercial beers out on the market, but the most recent one is called Cool Beans, and they're all through a microbrewery in Edinburgh called Barney's. So as I've said, making alcohol only uses the starch. So then we're left with the protein in the co-product. I guess as expected, faba beans are higher in protein than barley. So we're putting more protein in, so we get more protein out. So this brewery, typically their co-product has a protein content of 18%. But as we replace more and more of the barley, the protein content goes up. And as protein increases, the value of the co-product also increases in regards to animal feed. So we've taken some of this co-product and we're performing different feeding trials. There's been aquaculture trials and poultry feeding trials. Right, so that's brewing. So we successfully proven that you can add in legumes to beer without negatively impacting the taste of the beer. And that's just only with faba beans. There's lots of other legumes such as peas and lentils that can be used to develop different flavors to the drink. So the next thing we want to look at is increasing the alcohol content and looking at distilled spirits. So the distilling process is very similar to making beer. The high level steps, we still have our raw materials coming in. We want to extract the sugars from the raw material and turn them into alcohol. Now, obviously in Scotland, it would be great if we could look at whiskey, but the Scotch whisky regulations do not allow the use of legumes to produce that spirit. So instead, we can look at making something that we call neutral grain spirit. Now, this is a very pure type of alcohol, distilled up to 96% in strength, and then it can go on to be made into things like vodka and gin. So again, you take your raw material, for example, wheat or potatoes, like we do at Arbikie. You complete that mashing process to extract and break down the starch. The sugar-rich solution goes on for fermentation, and then you distill it to evaporate off the alcohol and leave behind the water and the solid material as a co-product known as pot ale. Okay, so again, we are proposing that legumes could replace these traditional raw materials. So far, I've been working on peas, but this time, however, you can use 100% replace the normal materials. There's no need for the barley or wheat or anything for flavour because we're making a neutral, almost flavourless spirit. So we did lots of small scale trials on peas and successfully showed they didn't impact the taste or chemical analysis of the final spirit, and that they sort of could go on to be used to make vodka, gin, or any other flavoured spirit. Again, as with the brewer's draft, distillery pot ale is richer in protein when peas are used. So you can see here our typical protein content of potato and wheat pot ale. And then when we use peas instead, there's a 48% increase in the protein content of this co-product. So once again, increasing the value. So we've taken all this information and we've successfully now released 2 commercial products, a gin and a vodka, and they're both made entirely from green peas. So they're sold under the brand name Nadar, which is Gaelic for nature. They're the world's first spirits to be made from peas, and they're marketed as climate positive. So how can we say that they're climate positive? Now, it's really through avoidance of CO2 emissions. So I've already discussed that you avoid having to use nitrogen fertilizer in the use. So those emissions are avoided. And again, with the rich co-product full of protein, you can reduce the need for imported soy for animal feed. So the benefits of using peas versus a cereal such as wheat were independently assessed by a group of experts. They completed something called a life cycle assessment of these gin made from these 2 raw materials, comparing the footprint of 1 litre of packaged gin produced either from wheat or peas. Okay, so the assessment quantifies the environmental impact of each gin type, including all the inputs required to make a final bottle of gin. So that's not just the raw material, but from growing it, your packaging, and all the processing steps in between. So this has been published in the Environment International Journal. And this table here shows 14 environmental impact categories that were looked at, and found that a pea-based gin had a smaller footprint in 12 out of the 14 categories. Okay, so that was just a very quick overview for the non-brewers and distillers out there of the process steps involved in using legumes, but hopefully aim to show you that legumes have the potential in being an alternative to inorganic nitrogen fertilizer and supporting other crops. They also can offer a more green starch source to the alcohol beverage industries. And in turn, you then get a protein-rich co-product, which can be fed to the aquaculture and poultry industries, or even human nutrition as well. So that's it. Legumes, you can see, have the potential to feed our soils, our animals, and ourselves. Thank you.
Perfect. Thank you very much, Kirsty and Derek, for both very interesting presentations that you have. We now move on to the question and answer session. And so, if you at home, if you hover over the bit at the bottom, you'll see that there's a Q&A section, so you can put your questions in there. You can put them in with your name, or you can make them anonymous, and then we'll just read them out. So starting off, we've got some interesting questions already through here. So I'll read this one out for you, Derek, and then you can answer it for us. So considering the developing economies where population is increasing, should biorefinement be encouraged there, and in particular where post-harvest losses of food crops are still on the increase?
Yeah, I think there's an absolute win to be had there, and it will still need some sort of investment to buy pieces of kit, but actually some of the stuff that may be deemed not a great value can actually go through fairly rudimentary fermentation, like lactic acid fermentations, to upscale the value of these things. I think it's just exposure to what can be done to these developing countries, and actually technology that might be deemed to be too old. I mean, I don't want to be colonial in this, but technology is often replaced much faster here, despite the fact it's still working. So there's technologies that can be bought very cheaply that would allow biorefining to work, to progress very fast. And actually, I think you're finding big companies are thinking about developing countries as feedstocks already. So this probably is going on. I know in certain places like different parts of Thailand and things like that, it's going on.
I think there's also a balance between getting that right with also making sure that the food is stored in the correct manner, so you're not having all these food losses.
Yeah.
So that's a really interesting question. Thank you very much. And another one, this one's for Kirsty. Does the use of legumes impart any flavour to the resulting product? So you said the Barney's beer didn't, but what about the gin?
Yeah, so we're turning in something called neutral spirit. So here you're really distilling it so there's not much other than alcohol and water left. So in theory, the raw material doesn't matter. So no, the potato, the wheat, or the peas, if you distill it to over 96% alcohol, then it does not taste of peas, basically. And then you can go on and flavour it with botanicals and things that you choose.
So you're not getting that beanie legume flavour going?
No, don't worry.
Well, that's good. Okay, another question for Derek. What are the limiting factors for biorefining and vertical farming?
Well, both processes are relying on energy. So they will proliferate in areas where you can get cheap energy. Scotland's going to be on a winner here because I think we're the winner for renewable energy production in Europe at the moment. Or if you go to places like Northern Africa, or mid-Africa actually, you've got huge levels of solar you can use there. So it's always energy is the killer on this, with different levels of capital investment for what you want to do. I mean, the most rudimentary controlled environment agriculture system is a polytunnel. It's just plastic sheeting over the dome. But then when you add onto that maybe a ground heat pump or a solar thing, there's many more things you can do with that.
Very interesting. That's really good to know. And then the next question then is for Derek again. And it's vertical farming has been primarily focused on horticultural products, herbs, fruit and vegetables. How feasible is this for things like cereal crops?
So it's an interesting one. Vertical farming is changing from people's perception of it was very much a binary. You're either growing outside or you're growing in vertical farms. What you could find vertical farms helping field agriculture for is creating the next set of varieties. So breeding involves crossing up parent crops. You grow them outside, you pick the best ones, and then you cross again. vertical farming allows you to put a crop through multiple generations within a year. So we can use it for what's called speed breeding. We can probably get barley going through 4 generations in a year. So your speed to create a new variety that will work outside could be cut back enormously with savings on, well, not having to grow outside. So you're creating your best set of proto varieties inside, and then you grow them outside. So all cereal crops can be done that way. And actually we're doing some work on barley, rice. We've even got potatoes in the vertical farm for producing seed potatoes. You'll never use it for a production system.
Yeah. That's very interesting to see the use of it in different manners from just the food production. The other thing that I'm picking up on that, then, if you're doing particular herbs, fruit, vegetables, etc., you can then perhaps have smaller varieties that you wouldn't necessarily find that you perhaps might make more economical to grow. Is that something that you could?
Yeah, I mean, I've got a project, an Innovate UK project with some companies where we're looking at heritage varieties that actually don't perform very well outside, but their taste is absolutely fantastic. So now we're growing them inside. We don't have to worry about disease and bad weather because we are the person that controls all that. So you can actually see some really interesting new flavors coming through. What we want to do now is change the architecture of these crops. So I was chatting to Kraft, and they were saying if we could grow raspberries in controlled environment systems, particularly on a really small crop, they'd shift their whole frozen raspberry use to that. That means they can guarantee quality, as I was saying. Now, 10 years hence, 20 years hence, you'll get the same quality going all the way through, and no loss.
Sounds too good to be true.
It does, but it's not.
Another question for Kirsty then. What is the optimum ratio of cereal crop to leguminous, I can't pronounce that, crop to avoid off-farm nitrogen inputs?
The sort of typical, it's still an area of research, but there's lots of farms this year involved in a farm, like a larger scale trials, and we're kind of working on this 60-40 ratio. So 60% barley to 40% legume. It's a James Hutton project, a Horizon 2020 project, looking at different intercropping and ratios. So it's still under study, I guess, but yeah, 60 and 40 seems to be the go for.
And another one for you is, could you not use the whole pea rather than just the kernels? Pea pod wine is an old country kitchen favourite after all.
Yeah, so no, there's no starch in the pot. So we do use whole peas in regards to the kernel and the skin of the pea, I guess, but not the pod. Yeah, there's not the starch quantity in it, and it would be harder for us to process. So we use combinable peas, so they're dried in the field. So at this point, the pods pop open naturally anyway. So but pea material itself is very valuable for it's a nitrogen source in the field.
Yeah.
For the next crop.
Just put back into the ground again.
Yeah.
Okay. Interesting. And then another one for Kirsty is, how about the cost of substituting beans to starch over other raw materials for production? Is there a remarkable difference in costs for industries or not?
No. So we did a comparison for the bean beer, and actually a ton of beans costs less than a ton of malted barley. You do need to add some things like enzymes that they don't have naturally, but even with that, they're comparable or cheaper than malted barley. So
actually a cost saving.
Yeah.
Going on there. I presume this one's for Derek, I think. Do you think that the government, well, I'm going to pose this a slightly different question. Do you think the government should provide grants for small farmers to adapt to change their systems?
I think you'll see with coming out of Europe and CAP's going to disappear, there are different support mechanisms will come in, and there's the strong suggestion that one of these support mechanisms, grant, subsidy, whatever you want to call it, will be based on innovation and sustainable production systems. So I think support mechanisms, the existing support mechanisms will morph to support that, I think. On pure grants, there are ones out there already run by Innovate UK. If you're creating waste on farm that you think can be valorising it to something else. Zero Waste Scotland has a whole accelerator programme that's amenable to that. If people have got ideas and they think they want to run with it, just give me a shout. Emails at the end.
Good. That's good to know. And then the next one, I think, is again, probably for both of you, actually. An engineering students did a study which they claim showed that fermenting the residue sugar from sugar beet extracted pulp could yield commercially viable fuel alcohol. At that time, the person pointed out that the pulp had been wet heat treated, so is a good substitute for enzymic hydrolysis and thus increasing alcohol yield. Is that worth trying?
So you can make alcohol out of sugar beet for sure. I'm not sure what the wet heat treat method is. You'd still need something to break down the starch.
I presume the wet heat treatment would be.
I think certainly for sugar beet would be viable. I mean, you've got the simplest thing to convert straight to alcohol. It's a balance between what you're using that sugar for. So I think sugar beet will be resurrected in Scotland because we're doing a lot on that area at the moment because it'd be a fantastic crop. We used to grow it up until 1972 in Cooper, basically where the oat mill is. But the market's not going to be the same. It's not sugar going into shortbread, it's sugar going into your car. At the minute, we've got E5. If you've driven an unleaded car, you've got E5, 5% bioethanol. It's going to go to E10 maybe next month, actually. We import all of that from France at the moment. So there's a market opportunity there on import substitution. And what it would create is a new break crop in farming because my gut feeling is oilseed rape may disappear because they can't control disease on it. Sugar beet may give another opportunity. So we're chatting to every point in the supply chain there. The sugar pulp bit is right, but you have to balance the energy you're putting into processing it to the value you're getting out, which is why you've still got sugar in the pulp. Now, you can use that to feed animals, but actually there's a company called Cellucomp in Fife. They convert sugar beet pulp, primary cell walls, into fairly sophisticated thickeners for paints, things like that.
That's a wonderful company. They also do it from carrots as well, if I remember.
Yeah.
So another question for you, Derek, is why do we not see more biorefining being done if it's as easy as you have demonstrated?
You've got to buy the kit. People are innately conservative when it comes to buying capital. And the problem with biorefining, I would say, is it gives you, in people's mind, I need a piece of kit to make X. Now that's easy, I'll buy it to that. But if I get a piece of kit that I can make A to Z as well, and we'll work with multiple feedstocks, people think, must be something wrong with that. That's too good to be true. And what you need in biorefining is an innate understanding of chemistry, physics, natural products, and economics. So it's an area where you actually need to bring together not big teams, but teams that understand the different aspects. You're moving from a linear process to one where you may be dealing with 12 to 15 different feedstocks throughout the year.
Mm-hmm.
So you need to know that well. So it's probably a knowledge-based thing.
I think also it's whenever you get this with companies, they always look at the risk associated with it and the return on investment. Yeah. So an interesting one, that one. The other question is for Kirsty. Is it harder to process peas compared to more common raw materials? So what's your experiences of that?
It's yes and no. Like any raw material, you just need to really understand its starch content. So then you get the right temperatures and enzymes to hit it. You get the whole process is okay, but you do get less alcohol per ton. So there's financial consideration, but then that's balanced out with getting more for your co-product. And obviously the environmental benefits. If you put a price on that, then that's also good. So it depends. You just need to understand the raw material basically, and then you'll be able to turn it into alcohol.
Good. And then another one for you, Kirsty. In terms of reduction of fertilizer, how much less do you use using pea rather than a field of wheat with brewing?
The peas don't need fertilizer at all. So
not.
Yeah.
You get a complete reduction of fertilizer.
Of nitrogen fertilizer, yeah.
For Derek, about flavours that could be the outcomes of the several combinations of several factors, temperature, gas, composition, plant material, were they carried out sensorial, did you carry out sensorial analysis or laboratory tests, or has it not been tested yet? So.
We've done sort of preference testing, which is sort of the easy exit for that one, but also followed it up by things like GCMS and LCMS, so we can absolutely tell you they are different. So when we started playing around with things like basil's a good one to play with because it occupies 40% of the world herb market, so that's a big target. We could make basil so unpalatably strong you couldn't eat it. You might think, well, why would you bother doing that? But if you're processing for pesto, you can process a smaller amount of biomass. So being able to really play with the dial, how far can you turn it around before you break it? And we also played around with things like, if you're growing iceberg lettuce, I defy anyone to get a taste of iceberg lettuce. But we played around with it and created a distinct taste in iceberg. Same genetic material, but changed the environment. Physically, it started to have leaves that went like this. So we could create a new product from exactly the same germplasm just by playing around with the lights.
You need to come to us and do some sensory analysis as well. Yeah, I'll give everybody a quick minute or so, well, not a minute, but if anybody's got any more burning questions, we're getting to the end now. We've got a few more. For you, Derek, does Scotland have any specific advantages in any of the applications that you've identified?
Energy. Well, Scotland's size makes it interesting because I think we're at a size that's analogous to places like New Zealand, Denmark, that you're small enough that everyone's close enough to work together or fight, depending on what area you're in. But that makes you fleet of foot. What Scotland does have that many of the other ones don't is this renewable energy aspect. So Scotland can be both a production country, but a demonstrator platform for the world. And there's very few other places I think can offer that opportunity. And when you've got things coming on stream like the new hydrogen economy, and basically you're going to have huge wind, instead of rigs offshore, you're going to have huge turbines offshore, and they'll be converting that water power, that wind power into hydrogen and pumping that back down. The potential for growing climate positive food is just enormous.
An exciting time, isn't it, moving forward? I think we've really got some powerful projects on our way in Scotland. So well done to that. And I'd like to thank both of you very much for participating in this and coming out of your busy schedules to talk to us today. So thank you very much for that. I'd also like to thank everybody from that's come here and watched us today, and we've got people from all across the globe that are attending our webinar, so brilliant. If we didn't manage to answer your question, please contact the speakers directly, and their details should be on the screen now if you're looking at them. And we will share the recording of the webinar, including the Q&A session, to everybody who attended today via email and on our website. If you'd like to catch up on any past IFST webinars, please visit www.ifst.org/webinars. And before we log off, can you please make sure you fill out the short survey that will appear, which will launch after the webinar ends. Next slide, please. And finally, our online spring conference, Food Science and Technology, Thinking Smart, Acting Smart, runs from the 26th of April to the 7th of May. We've got some great speakers, great chance to network with fellow delegates and visit your exhibitor booths and take part in some question and answers and polls. So really do think about joining us there. There is a link to our conference page with more information at the bottom of the survey, so please do consider doing that. Again, thank you so much, Derek, Kirsty and Ruth, and everybody watching today. I think it's been a really interesting day, and I think we will look forward to doing more in the future. And that's us. Thank you very much, and goodbye.
Thank you. Bye.